All right, folks, good evening. Welcome to today's session. Today is January the 10th, 2024. We are here at Support Vectors Meetup. In this meetup, we plan to cover the LoRA family of fine-tuning methods. This request to cover it came from some of the participants who said, could I go over it? And so I'm sort of honoring the request of the community. A little bit about Support Vectors. We are here in Silicon Valley in Fremont. We are into AI training and AI projects. It's an applied AI lab. Those of you who are close to Fremont, I would invite you to attend it in person. If you do attend it in person, you will welcome you with good refreshments, I promise you. And with that, let's get started. Once again, please be aware that you are on record for the first half of the session as we cover the paper. Please do engage with me as I discuss this paper. It is supposed to be an interactive session. A little bit of a background. This work and a whole lot of similar work stems from a core problem. The problem that people face, or rather the set of problems that people face are, first, when you train a model, especially a large language model, let's say that you train a LLM, the size of the LLM is huge, right? It's a big size. Typically, I mean, it's getting bigger and bigger. Let's say that you take, for example, the most popular open source LLM is Llama. Llama 2, let's say, its full size is 70 billion parameters. That would be considered bizarrely huge just a few years ago. People wouldn't have imagined creating a model that big. And yet today, we don't think much about it because GPTs now, they come in size, they weigh in at 175 billion parameters or even more. GPT-4, with all its parts, I suppose, is a trillion parameter model. So the models have become extraordinarily big. The rationale for creating big models has often been a topic that we covered in a previous discussion. We find that as you scale up the model, their capabilities increase. They sort of things that smaller models are not capable of, the larger models gradually become capable of, right, at different scales. And so there is a huge temptation to create larger and larger models and see if some of the more intractable problems do become solvable as you scale up the model. With that being there, that is a good thing to observe with these large language models, and hence the word large. There is a problem though. The bigger the model you create, the more hardware resources it takes to train it. Right? As you know, to train these contemporary models, commercial models, hundreds of GPUs, if not thousands of GPUs, have been employed. Right? Those models took training or the pre-training phase. So let's write it down. Pre-training is extraordinarily expensive in hardware resource needs, in time to train, and in the data required. The bigger the model, the general thing is you need to bring more data. And we covered this topic the last time, that why we do that. Now, Fortunately, we tend to these days get or inherit these pre-trained models, at least the ones in the open source. Certain companies, certain research outfits are generous enough to donate it to the open source community. For example, you could go to Hugging Face and download these models. We all do that all the time. Now, there is a question though. Will that model run? Downloading is okay. Disk space is plentiful. We can download those models, but will we be able to actually run it? Or for example, if you get a 175 billion parameter model, do you even have that much RAM in your laptop or your desktop? Quite often not. That brings up the question, what do we do? And now this RAM comes in two types. One is the physical hardware, the traditional RAM, the DRAMs, and then there is the VRAM, or the what is called HBM, high bandwidth memory, that is resident on the video cards or the video RAM. Video RAM tends to be orders of magnitude more expensive than the mainstream RAM that you put in your computer. And generally, if you get the cost, the pricing of GPUs or hardware accelerators is almost completely, large part of the price depends upon how much of the HBM or the video RAM it contains. Now, as of today, for example, most of you, if you are playing around with AI models, you have access to a 4090. If you're lucky, perhaps you have access to two 4090s, RTX 4090 as your GPU. Now, these 4090s have 24 gigs of RAM. If you have two, it is 48 gigs of RAM. You realize that with 48 gigs of RAM, you're still not able to load some of these very large language models. But then we have, suppose you could load it. You load it, for example, you could load a 70 billion parameter, right? Llama, which is doubtful, but let's take something simpler. Let's take a 7 billion parameter Mistral or Llama, or something like that. A much smaller model. You feel pretty good about it. Hey, you could load this model into your GPU, or it is a bird, or it is something like that, a big one of the bird family models. Whatever it is, these large models, you load it into your GPU. Realize that when you pre-train a model, it has been trained using unsupervised learning on a large variety of tasks. You have a question?
Sorry, does that say hardware resource needs?
Hardware resource needs, yes. Right. So when you load this model, it has been trained on a whole variety of general tasks. Right. It may solve your problem, but quite often you need to further fine-tune the model, which means that you need to, for example, you may need to do domain adaptation. If you're in the medical domain, the medical is a language in its own right. And so you may need to do further adaptation of that model. Or you're talking about finance and you need to adapt it. Or it is task-based adaptation. You are doing some very specific thing, a particular kind of question answers, or you're tuning it to respond in a certain way, or you're doing search and you want to do semantic search and you want to fine tune the model. In each of these situations, further fine tuning is needed. Now, there's a general rule of thumb, which is the 10x rule of thumb that people keep quoting, which basically means that for you to, in general, fine tune a model, whatever resources it took to load the model, you will, in a sense, require about 8 to 10x the size, 8 to 10x the amount of resources to fine-tune it. Now, just to recap, fine-tune means it's supervised learning or some form of it. You take a data set of your own, your data set, you use it to a pre-trained model. Let me take a pre-trained model pre-trained, and you pass it to come up with, after a few epochs, let's say epochs of fine-tuning or just basic training, tuning, which basically means you take a pre-trained model and you train it. on your data in a supervised manner, what you will end up with is a fine-tuned model. Let me call this fine-tuned FT, a fine-tuned model. The problem is this journey from here to there, this particular journey requires lots of hardware. It does not require the same degree of hardware as is needed to pre-train, but it still is a significant amount of hardware that you need to feed in, right? Typically, for example, people will take a four-way or a 4 GPU or 8 GPU A100s, a box with 8 A100s, and say, all right, this might prove sufficient for many, many needs of fine tuning. And that does generally happen to be true. Go ahead.
Sorry, what kind of hardware?
These are inference servers. These are computer hardwares that contain a lot of these math accelerators. These are usually GPUs, like, for example, NVIDIA. A common one of them is NVIDIA A100, which contains 80 GB of VRAM, right? Or it could be H100, both of which contain 80 GB of this. Now, these are pretty mighty machines. For example, and then the more consumer grade hardware would be, so you would need 8 cross this, typically for fine tuning. So as you imagine, fine tuning, of taking a full model and fine tuning it with your data can be rather expensive in terms of compute needs. Fortunately, when you fine tune, data needs are not prohibitive. Like we looked at 3 factors: hardware resources, time to train, and data required. The data required is relatively modest. Time to train is also relatively modest. But your biggest hurdle is, will you even be able to load that model in memory, right? In vMemory. What is the alternative? You say that, oh, I'm going to train it on the CPU memory, because most of us on our workstations these days, we carry 256 GB of RAM or 512 GB of RAM. You can even, if you're generous, you can stick in 1 terabyte of RAM. And you say, well, I have enough RAM. But actually, there the trade-off is you have the enough RAM to load the model, but computes will be very slow because the general purpose cores in the CPU are not designed for AI in particular, though that's gradually changing now. The hardware makers, Intels of the world, are doing that. And also there is the situation, I must also say, as of today, is in flux. For example, you have the two companies have unified architectures. The Apple has its Metal, in which they have a unified memory, and they have this big CPU with a lot of neural cores and so forth. They're trying to catch up, though they still have a distance to go. Likewise, AMD has a sort of a unified architecture that they're coming out with. So things may change as we go forward, but as of today, if you use the general purpose memory in the box, and you use the normal CPU, the situation is your training or your fine tuning will go very, very slow. Right? Now, again, as I said, many innovations are coming in. Very recently, there was a paper that found an efficient way to tune these large models, fine tune it by studying the weights and biases and looking for hot and cold weights, weights that actually are very active during fine tuning or training, and weights that it determines are rather cold. They're not going to change much. Now, if you remember, when you train a model and you do the back propagation and updates, the biggest thing is that you bring blocks of weights into memory or into the GPU's active memory, and you do, or the actual cache, you do the computation and you swap it out. A large part of the time goes in just swapping in and out the blocks, the weight blocks. Now, along similar line of thinking, what it does is, what it says, suppose we did the rare computations, the weights that almost never get multiplied or updated. Let's keep them in CPU memory, and let's keep only the hot weights into the GPU memory, right? And they have done that. It's a very recent work, and it seems that they have achieved quite a bit of success in fine-tuning these models with uh, consumerish grade, let's say, hardware, right? With the so that is a bit of good news, but this is a long journey. There are lots of people who are trying efficient ways to fine-tune the large language models on reasonable hardware. By reasonable hardware means it's the kind of hardware that you and I can purchase without breaking the bank, right? And that for the open source community is a very uh, strong need, because the open source community and the academia, for example, does not often have access to very expensive hardware that corporations have access to. So in that strain, with that as a backdrop, this paper is quite interesting. It is an old paper by now. It came out, as you can see, a while ago, and it opened the door for fine-tuning a model with in a very fairly efficient way. Now, before that, also there were you may ask, well, these LLMs, can we not just fine tune it, in quotes, fine tune, by writing better prompts? Right? We do know that, and by prompt, that training it with a few examples in the prompt itself, the few short learners. Right? You say, I can make it do better by giving it a better prompt, better instructions, giving it better examples. And yes, that works. That should perhaps be your first approach if you can get away with it. The trouble with prompting is it takes you so far. Also, prompt-based fine-tuning has a sort of a demand that prompting LLMs are today, even today, fairly sensitive to the language of the prompts. Sometimes a very small change of language of the prompt leads to drastically different quality of results that you get. So, and for other variety of reasons, people have always looked for real, honest fine-tuning. Let's go and do a supervised fine-tuning of the model. And how in the world would you do that? That's a question. So to do that, this thing, actually the roots of this paper, or the core intuition for this paper, actually comes from its first reference. So I would like to take you to the first reference. I didn't load that paper, but it would have been worth quoting, because I would suggest that if you are quite a bit interested, it helps to go and read this. And I'll just mention the title of this paper. It says, Intrinsic Dimensionality Explains the Effectiveness of Large Language, of Language Model Fine-Tuning. So what is this paper trying to say? It asked this question, which was a puzzle. From a machine learning perspective, remember, it's a general belief that the bigger the model, the more data you need to train it, isn't it? Because you're looking at a very high dimensional space, right? All those weights and biases, they represent a hypothesis space, a parameter space that is of an extremely high dimension. Each of the weights and biases is its own axis, isn't it? So suppose you have a model with 5 weights and biases, let's say, well, then you have, well, that's too small a number, let's say 100. Then you have a 100-dimensional space. We are talking about spaces that are in billions of dimensions. And yet, we are trying to do, if you think about it from a theoretical perspective, we are trying to do gradient descent in such a very high dimensional space. Common sense says that you need lots of data to not have overfitting, not to have a proper regularizing effect, for this model to learn anything whatsoever, not just memorize your input. Right? We do that. And yet, paradoxically, you can take a pre-trained model and take a very few a data set that's whose cardinality is, let's say, a few hundreds or thousands or 10,000 or something like that, which is nothing compared to the hundreds of billions of inputs that are needed to pre-train the model. And yet, with a vastly many orders of magnitude smaller data set, we are able to fine-tune these language models. there's transformers. And the whole question is, how come that we can do it? What is the intuition? What is the mathematical reasoning behind it? Right? And the explanation, in some sense, goes to this. What this paper, the intrinsic dimensionality, explains the effectiveness of language model fine-tuning. It makes a very interesting observation. They asked this question. First of all, they had the question of what is intrinsic dimensionality, and to understand that gives you the main insight of this paper, this LoRA paper that we are going to do. It is this. See, imagine that you have a model, and this model internally represents data. Is it really using all the billions of dimensions of the data, or is the data, or is its internal representation? Whenever you get an input, what is it representing the input as? Or another way of putting it, a very not exactly correct, but very close intuition is, think of it as an autoencoder decoder. Imagine that if every model were internally behaving like a autoencoder, right? Hypothetically, just go with argument, though it is not. A transformer architecture, for example, is not inherently, you can't map it to a encoder decoder. But let's say that you could. Right? Every model you could think of it like that. Then what would happen? What does the encoder do? Encoder, in effect, creates a lower dimensional hidden representation in a much smaller dimension. Let me just call it R. Suppose D is the input, X belongs to a D-dimensional input, which is very high dimension. It internally projects it to a low dimension. And then this is your encoder function, fx. And you have a decoder function, and this is z or h, z of h, that reconstructs x prime, right, back to, let us say, back to the D dimension. So what happens is a huge data vector goes in, a huge data vector comes out. You train it to match, the output to match this. But internally, you have created a bottleneck. You have forced the autoencoder to learn a lower dimensional representation. Are we together? Right? In other words, what you expect is that the x prime that is equal to the g of f of x, right, should approximately be x itself, input itself, output, right? But when you do that, you have an issue. How in the world can you do that? You have gone from a vector that was, let's say, 1,000 dimensional, and your dimension R, let us say, hypothetically, is, and for the sake of argument, I'll take 4. How do you take a 100 dimension, 1,000 dimension vector and compress it down to 4 dimensions? The only way you could do that successfully and reconstruct most of it, you lose something, is to say that the data internally, there's a hidden representation. There is a hidden space, abstract or latent space, which is actually only 4-dimensional. And this machine has somehow learned to encode the data into that low-dimensional space. Are we together? And that low-dimensional space has a compressed representation of the data without much loss. Are we together, guys? That's the core intuition of an autoencoder. Right? Now, bringing the same thing to that of a large language model. What happens is that in the large language, in this language models, and I keep using the word large language models because they've all become so big, and LLM is the more common word we use these days. So you take this LLM, it has this bizarrely huge number of parameters. It represents a huge space. And the question worth asking is, and then, by the way, this is a whole parameter space. I'm just giving you the intuition, but we'll go block by block. We'll go transformer head by transformer head in the LoRA. So let me put that caveat as an important thing. But generally, if we believe that when data goes in, it is transformed by a matrix. Let's say that we do this. Let's say that, for the sake of simplicity, assume that we have a square matrix. It need not be square, actually, and this paper doesn't make it a square. Let's say that you have a D cross D matrix of weights belongs to D cross D dimensions, right? So D rows and D columns, right? D rows, D rows, D columns. It's a matrix. It is there. And so what happens? An input goes in, X, and an output comes out, right? Which is, let's call this matrix W, WX. Are we making sense? You get the output. But let's say that this particular square matrix, if you could internally say that, and this is the observation that this paper makes, it says that even though the dimensionality of this matrix is high, it looks like a d-dimensional matrix, right? Or by the way, it need not be square matrix. The generalization of it would be D cross K. A D goes in, K comes out, right? The k-dimensional vector comes out. So it could be a rectangular matrix also, but let's stick with squares because squares are intuitive. Now, there is something in linear algebra. It's called the rank of a matrix. Rank of a matrix. Now, what in the world is the rank of a matrix? The rank of a matrix is something very interesting. It says that a matrix may have redundant information in it. What's an example of a redundant information? Suppose I have numbers 1, 2, 3, 7, 2, 1, 2, 4, 6. Now, look at this. Does something look as though it's repeated? Right? If you look at this column, so if you look at column 1, column 2, column 3, you notice that column 3 is equal to 2 times column 1, isn't it? So you say, in other words, that there are certain columns which contain information that can be derived from other columns. When that is true, you say that this matrix has redundant information, that the true information is actually only two-dimensional, right? It is two column vectors. You need just C1 and C2 are the real ones. You say are the real info. It's a very intuitive way of looking at it. This is redundant. Would you agree with that? And so you say that the rank of this matrix is just 2 columns, right? It is rank 2. I hope I'm getting you the intuition, right? So the question that is asked is, when you look at a weights matrix in a neural network, what is its intrinsic dimensionality, right? Now, if you were to think of it, simply put, if you think of this matrix, that internally, if you could magically reduce this matrix with sort of a autoencoder-like structure, imagine, just in your mind, imagine, could it be replaced with that? How much information would you lose? And people have done studies and they have found that actually you don't lose that much information, but obviously you don't, by the way, this is just hand-waving arguments, guys, giving you the intuition. Do not at all think that directly you do autoencoder here, but that is the intuition that is here. The people found that the intrinsic dimensionality, or the true dimensionality of the weights and biases, or that particular weight matrix, that is needed to do the task. In languages, it is what? To predict the next token or to tell sentiment analysis or so forth, is usually much lower than it appears on the face value. Means the matrix has redundant information. And there are many ways of seeing that. For example, you can do a random projection subset. You can just randomly project the matrix out to just a few subset of weights and see, can you get away with just using those for your computation? And quite often you are able to just train those and get away with it, or fine-tune those, or run with those and get away with it. So that was the basic intuition behind this paper. It's really worth reading because I feel that papers like this lay the foundational ideas. And it is this paper that inspired this LoRA thing. What LoRA says is something, with this intuition that I mentioned of an autoencoder, now to you, the LoRA thing will look very straightforward. Before I continue any further and even read the paper, does anybody notice in this figure here anything that anything that is reminiscent of a, not exactly that, but is reminiscent of, apologies, I made it too big. Yeah. Does anybody see something here? I don't know. That is somewhat reminiscent of a encoder decoder. Yes, you see that right here. If you look at this area, what does this look like to you? A looks almost like the encoder part, and B sort of looks like a decoder part. Do you see that? And if you get that intuition right, now we will ask, okay, how does it tie it to this whole business of fine tuning? That's a question we'll ask. So the way they do this and is even very, very simply argued actually and beautifully argued. One nice thing about this paper is it is just one beautiful mathematical argument. That's all it is. And then experimental results from it. And, it's one of those most beautiful moments. You have a good idea, good mathematical idea, and you try it out in the laboratory, you try it out with data, and the empirical results just resoundingly support you. They just come out completely in favor of the idea, almost telling you that, yes, this is how it is, right? And that's the sort of feeling I got when I first read this paper, and obviously amazing work. So let's look at what it is. What they are saying is that, see, you have the pre-trained model is a matrix of weights and weights, right? Forget biases, we'll take the biases. So when I say weights, include weights. So suppose you have a W naught is the pre-trained weights of the neural network, or part thereof, As it happens, in the context of transformers, we mean specifically the attention heads, right? And we'll come to that, not the entire network as one giant W, because it goes through successive phases. All of us know the transformer architecture. So we'll take this. So what is the typical full fine-tuning journey before this concept came up? What you would do is you would give it data D, right? And fine-tune, and I'll use the word full fine-tuning of the model. So you will go and get yourself a big server with 8 A100s or something like that, right? Beg, borrow, steal. And then you would have a model W. So let me just call it the fine-tuned model. So now, if you ask yourself this question, and this is the question to ask, what is the gap between W fine-tuned minus W naught? How different is the fine-tuned model with respect to this, right? Or another way of putting it is W final, actually, they just use the word W here. So I'll also just use the word W. W is equal to W naught plus delta W. Oh, by the way, the paper uses delta, the capital Greek letter, and I tend to use the little one mostly as a old physicist habit. So please forgive me, it's the same thing. So this is it. You see, wait. Now the question is, how much information this delta W contain? The first intuition is D is a relatively small data set, isn't it? It is not of the same size as the pre-training data, which is ginormous. You take all of human knowledge and feed it into the LLM, right? But your D, a data set, is whatever you have in your company for that particular task, right? Let's say 10,000 records or whatever it is, 100,000 records, or even just 1,000 records. So what it is going to do is, assuming that your model is well-trained and it's along the same lines, it should not destabilize that model, the weights and biases, too much. It should cause small perturbations, small changes. Would you agree? And not only small changes, those changes may not be everywhere. Now, we already know that these, the initial weight matrix, W naught, is intrinsically of a lower dimension, and so it's really, you don't need to go change all of them, right? Truly, you don't need to go change all of them. That's prior work to fine tune it. But let's say that it's changing. You're making small perturbations on that. So inherently, you would imagine that. Think from scratch, if you were just building a model, imagine that you're just building a new model on just this data set, D. Then the size of the model should be comparable to this data set, isn't it? Because that's what it is. Imagine that you're building a delta W model. It should be comparable or commensurate or with the data set size with which you're fine-tuning, which is not large. So the intuition, therefore, is that somehow the number of weights and biases, the number of weights inside this delta W shouldn't be too many, isn't it? It shouldn't have too many weights. But there's a problem. See, look at this. If W naught, and by the way, I'm simplifying it from the paper. If it is D cross D, a D-dimensional vector goes in, D-dimensional vector comes out. And I want to do that just because I want to use the sort of autoencoder's intuition there. Then you would agree that delta W also has to be the same dimensionality. D-dimensional vector goes in, D-dimensional vector comes out, isn't it? Because, right, this part, because ultimately the two add up to, this is also D cross D, so this also has to be of the D cross. But there is a thing, this is a full giant matrix. And yet you know that you don't need so many parameters. Are we together? You don't need so many parameters. Your intuition is you don't need so many parameters. The intrinsic dimensionality of the matrix is low. So what is the easiest way that you can reduce the intrinsic dimensionality of the matrix? You can say delta W is basically like an autoencoder. Does that make sense? Right? So you, and by the way, you make it a matrix, somewhat like even simpler. It's just a matrix A, first B and A. Actually, the picture says, let me get the naming correct, which one it calls A and which one, yeah. A is the input. Let's say that X goes in. This is A, B, right? And then you get the output, right? And what do you do with the output? But there's a problem. W, like, so think about it this way. This is very elementary algebra. When the model is fully tuned, fine-tuned, there'll be a final weight matrix, right? But if this weight matrix can be thought of as the combination of the original weight matrix plus some perturbation of the weight matrix, right? This times X. And further, if you say that let's leave W naught alone, but this we can represent it as, and I believe I don't want to get it backwards and forward. Let's see how they wrote it in their paper. BA. Yeah. So first you apply A, of course, A to X, and then you apply B, right? So W dot X. I can write it like that, like this, guys. This is very elementary, right? We just decompose the delta W into a matrix multiplication between B and A, right? And now comes an interesting thought. While this looks like very elementary algebra, it has far-reaching consequences. Why does it have far-reaching consequences? What it is saying, if you look at this bit, it's saying something pretty interesting. It is saying that this is your original pre-trained, let's call it the base model, isn't it? The one that you downloaded, right? So what you can do is you use that only for the forward pass. Let's say that if you want to produce the output, W naught X, let me call it part A, Y0 is this. Let's call the part B, which is the delta part, comes from the fine tuning. Delta is the BAX of our input, right? And then the total Y, the total prediction is Y naught plus Y delta. Except that this is there. Now think, what can we do? We don't know B and A. What if we did this? We froze this, freeze W naught. So freeze the original model, leave the original model alone, and basically say that when new data comes, it is only going to train A and B. In other words, train this just find the weights of these new matrices, the optimal weights of the new matrices. Any questions, guys? Is the intuition? It's a beautiful intuition. You're saying I'm going to keep the original base model there, and I'm using a superposition. I'm layering it together, right? I am saying that, okay, as the back propagation happens, so as you do the gradient descent from the loss, just backprop and update A and B, right? But A and B together, they don't have that many parameters. Let's say, and what do I mean by that? Let's say that the initial dimensionality was, I'll just say for the sake of argument, take 100, right? Let's say that the final dimensionality is, let's say, for the sake of argument, I'll take 2, right? Now, you realize that W is 100 cross 100. How many weights and biases does it have? 10,000, right? On the other hand, A belongs to 100 cross 2, B belongs to 2 cross 100, right? Now, what does it mean? How many parameters does A have? 200. And how many parameters does B have? 200. Total of 400 parameters. How many parameters does W have? 10,000. And that is the key part here. That's the whole point of this method. It says that you can create a much smaller matrix, 2 matrices, A and B, which you can load into your consumer grade GPU, your 4090, and you can back propagate the losses, use the fine-tuning data to just back propagate and learn A and B, the optimal A and B. Right? A very simple intuition. This is the saving of 400 params versus 10K param. Right? And it turns out, when you look at the results, one of the beautiful things that comes out is that sometimes it actually beats full fine-tuning. Right? But when you lose it, you don't lose. From experience, people say you lose a few percentage points compared to a full fine-tuning with lots of data. Right? So with that big background, let us walk through this paper a little bit more carefully. I'll read the abstract. It says an important paradigm of natural language processing consists of large language model, large-scale pre-training on generic domain data, and adaptation to particular tasks or domains. Adaptation is the fine-tuning part. As we pre-train larger models, full fine-tuning, which retains all model parameters, becomes less feasible. Right? In fact, if it is normal Joe like you and me, it becomes completely beyond us. Well, using GPT-3 175 billion parameters as an example, deploying independent instances of fine-tuned models, each with 175 billion parameter, is prohibitively expensive. Right? It's as simple as that. You take GPT-3 175 billion parameters, multiplied by a rough and ready number 10. It becomes 1.7, like 1750. Go get 1750 GB of RAM or something like that. Right? Now, that's considering that typical machines have about 80 GB of VRAM per GPU. 8 of them put together just make 640, right, per machine. 16 makes it 1.2. You realize that you're looking at very expensive hardware to fine-tune these machines. That's the main point. So we propose LoRA, low rank adaptation or LoRA, which freezes pre-trained model weights and injects trainable rank decomposition matrix into each layer of the transformer architecture. By each layer, by the way, and this needs explanation, greatly reducing the number of trainable parameters for downstream tasks. Compared to, then it goes on to say that compared to GPT, fine-tuning with Adam LoRA can reduce the number of trainable parameters by 10,000 times. Right? That's a massive reduction, and the GPT memory requirements by 3 times. LoRA performs on par or better than fine-tuning in model quality. And this part I found very interesting when reading the abstract for the first time. It goes on to say that on par or better on fine-tuning. Surprising that it can sometimes be better. Why? But in my view, it because when you reduce the dimensionality, you find the true dimensionality of the data, and that helps you. You sort of cut out some of the noise in it, and it brings about no additional inference latency, or very low additional latency. I won't read the rest of it. So it talks about a few key advantages of that. But before that, it talks about this inspiration that it got. We take inspiration from this paper that I just talked about, which shows that the learned over-parameterized models, in fact, reside on a low intrinsic dimension, right? So if you are looking for a intuition for low intrinsic dimension versus real dimension, here is one basic intuition I'll give you. Imagine a spiral. You know, we have those jumping spirals, right? Hopping spiral. So spiral. Now, the spiral lives in 3 dimensions, isn't it? But in reality, if you consider one end of the spiral as the 0th is the origin, 0 point, then any point on the spiral can simply be parameterized by a single value. And what is that value? How long you have to travel along the spiral to reach that point. Am I making sense? Right? And so the true or the intrinsic dimensionality of the spiral is just 1 dimension, even though the spiral is residing in 3 dimensions. Right? That's the intuition. Or if you have a page with things written on it, information written on it. Let's say you take any one page, I'll hold a page. Let's look at this paper. If you say information is everywhere, whatever it is, but it is actually in 3 dimensions, but data is only written on the 2-dimensional submanifold or surface here. So that's sort of the notion of you can have a high dimensional space, but things may, or what is of value may reside on a lower dimensional embedding. Right? That's it. So it goes on to say that that was the intuition of the previous paper. We hypothesized that the change in weights during model adaptations, which the delta W's, right, the perturbations. I also use the word, because this is language you may often see me use, perturbations. Perturbation of weights, delta W. Yeah. We hypothesize that the change in weights during model adaptation also has a low intrinsic rank, leading to our proposed low rank adapter. So guys, when you know the data may have a compressed lower dimensional representation, your basic intuition is to think autoencoder like architecture, isn't it? We're all used to it. And pretty much that's what you see in the figure. Wherever is the figure gone? Okay. Yeah, there is that. You see that, except that it's even simpler. You take a matrix, forget about activation functions and all of that. You just take that this weight and you replace this weight with a 2 matrix multiplications. Even simply think of it as a very, very oversimplified 1-layer autoencoder with the identity activation functions. As simple as that. That's pretty much it. And so it has. So when you do it, it gives you many advantages. Here are the 4 advantages they list out. A pre-trained model can be shared and used to build many small LoRa modules with different tasks. Right? Now, what it means is You can do many things with LoRa. And those of you who are playing around with, uh, you know, text to images like stable diffusion, etc., etc., you know that this is very, very common. What people have done is they have one LoRa to put lipstick on you, another LoRa to, I don't know, prettify the eyes, another LoRa that will give it a very, I don't know, maybe Van Gogh look to the picture, to the output. Right? And now what can you do? You can additively choose which of the features do you want in your output. You see? So obviously, since this paper was written, a lot has happened, and LoRa is all the rage. It is perhaps the most common form of model fine-tuning currently practiced. And people have created beautiful, beautiful libraries of these LoRa adapters that you can apply to base model to achieve really creative end results, especially for images and for other areas also, right? For text, for images, and for everything. Right? That's the beauty of it. So today, this thing looks this statement is obviously resoundingly true, what they mentioned in the original paper. The second point they make is LoRa makes training more efficient and lowers the hardware barrier to entry by up to 3 times when using adaptive optimizers. Adaptive optimizers, think Adam, right? So this is a no-brainer. If you have to load 200 parameters, you're much more likely to succeed to fit it into your GPU than if you have to load 10,000 parameters. Right? Common sense. Per like a matrix, and suppose there are many, many such matrices there, which will be, you have a lot of accumulated cost saving. So this point again is self-evident. Next point they make is our simple linear design allows us to merge the trainable matrices with frozen weights when deployed, introducing no inference latencies when compared to it. So this brings us to our next point. Suppose I have trained A and B, right? You already trained A and B. What can you do now? You could go back and create W is equal to W naught plus BA. You could go and create this, right? Together, compute this. This is just one single multiplication. In one pass, you can compute the complete new W, merged W. And so at inference time, you don't have to put the input through 2 parts. Here, if you look at it, the picture seems to imply 2 parts, that input X goes in, it goes through the base model on the left, it goes through the LoRa adapter on the right. Whatever comes up, you add the 2 up. But you don't have to do it if you have already computed and merged that and computed the fine-tuned W, right? Just training is expensive with this backprop and everything. You do that, then you multiply B and A, and then you add it to W naught to get the final W. And so then you don't have a latency problem, right? Whatever was the original cost of multiplying with W naught will be the cost of multiplying with W. They have exactly the same dimensionality, right? So that's the point being made in the third one. And the fourth one is LoRa is orthogonal to many prior methods that can be combined with many of them, right? Such as prefix tuning. So there is a whole field that has emerged. It is called a parameter fine tuning. By the way, for those of you who are participating in our upcoming generative AI with LLM bootcamp, which is starting on February 1st, right? All of these things will become very real because what we are doing as theory here, we'll be doing as labs, code, right? We'll be doing it with a lot of code, and you'll be doing that. And anybody here who is interested in that bootcamp, reach out to us. We can tell you more details if you're interested. But anyway, so this will all become very real. But this is definitely true. So in this field, parameter efficient fine-tuning, there are many methods. For example, soft prompting, prefixing, right? And so on and so forth. And we will go to the Hugging Face website and they have itemized 3-4 methods, right? Other methods. The good thing is that you can still do that, right? You can still do your prefixing, you can still do your prompt optimization, and so on and so forth. It doesn't prevent you, because at the end of it, what do you have? You have changed the inside of the model. Those techniques of how you feed in the data, what you do, they can still be applied. It's orthogonal to it. Orthogonal is independent of it. You can still apply those methods together. So that's the fourth point. Now, there is another point that it didn't mention, but that is actually pretty significant. See, every time, if you do a full fine tuning, let's say, where is a full fine tuning? Like you do this journey, suppose you do this journey, directly start training your data with lots of fine tuning data. When you do it with a lot of fine tuning data, what happens is there is a risk. What if your model starts forgetting things, whatever it learned? Because what if your fine tuning data is so different from the general data that went into pre-training that the model weights, they begin to make drastic shifts, right? And some level of unlearning begins to take place. That has actually been practical experience. Sometimes you burn through a lot of compute time and compute resources, and then you scratch your head, why is my model worse? The model has actually unlearned some things, right? And it has in some sense overfit your particular data set, but it gets pretty, I mean, the world of LLMs is very hacky at this moment. You have to see, just because you think it should work doesn't always work, right? So there's a bit of risk of unlearning. Now, the beautiful thing is, if your W0 is frozen, the base model is frozen, you don't touch it at all. You don't risk unlearning as much, right? You don't, that learning is there, it's frozen. You're just superimposing small deviations or small new learnings on top of what has been learned before. Does that make sense, right? So that's the point. That's an important point. That's not here. That's not here. But nowadays, subsequent to this paper, we have come to know. Now, it goes on to say things which obviously would be of value to you. So I'll just talk about this equation. This equation is self-evident. What do you want to maximize? Given your parameters, let's say that your model parameters are, well, we usually call theta, but this is a big theta. Means the set of all your weights and biases, right? This is this, whatever weights are there. What do you want? The probability that you will get the token that you want, really want, right? Versus the token that you have, and the token, I mean the input and the tokens that have been received prior, let me just call it prior, right? At a given time, the tth token, what do you want? You want that the right token, maximize the probability of the right token, isn't it? Your model should maximize the probability of the right token, given the input and the tokens that have been generated so far. This is the typical next token sort of a model. You want to maximize this probability. And how do you do that? You take the log of it, right? Log thing. The thing for a while, I mean, all of us have gone through the machine learning exercise, so we know the reason. For one thing, we can do the gradients of it more efficient, the log, the log gradient trick, and so log derivative tricks, and so on and so forth. So basically, this becomes more manageable, right? And you want to maximize that. So this part is a no-brainer, right? For all the inputs and for all the tokens that each input produces, because input will be a sequence of tokens, whatever output it produces, right? Therefore, the two signals. You want to maximize that. And what it is basically saying is that this task, which is the core task, you reduce it to the task of saying, okay, leave the initial weights and weights alone, but look at this delta and do the same thing, but just do it for the delta, right? The parameters in the B and A matrix, that's all. It's just a more concise mathematical way of saying it. Now comes so this method is there. Practical benefits and limitations. The important observation is how well it does with this. So if you look at this, let's look at one column. I won't go through all the metrics. Let's just look at this column. And then I'll just highlight the one that is LoRa. LoRa is here at the bottom, right? And this here, LoRa. So let's look at the, I think, Roberta model, base and large and this and that. What you notice is that number of training parameters in the full fine-tuning parameters, if you do a full fine-tuning, would be 125 million, large number, right? But if you do the LoRa way, it's just 0.3 million, right? So it is almost like 500 times more, right? Parameters. So there's a huge reduction in the number of parameters. But look at the performance. If you look at the performance on this particular benchmark, right, from 87.6 you went to, oh, what did we go down to? 87.5. Would you consider that a tremendous loss? You wouldn't, right? It's a pretty close, right? In another benchmark here also, if you look at it, very small losses are there, right? Very small losses you see. Now let's go down to the Roberta large from 90.2. Sometimes you notice, surprisingly, what do you notice for Roberta large? The score has actually gone up, right? Which really means that the Roberta large, for the task on which for this MNL1, the task that this benchmark looks at, it is truly, really over-parameterized, isn't it? And in a way, doing LoRa not only solves a practical problem, it also amplifies the learning because it finds a true hidden low-rank dimensional space where data resides. So this is its value. And this is also something interesting. There is another model, depth, I have to look what it was. But again, the performance seems to have gone up slightly. Generally, today we believe that you don't lose much. Sometimes you can actually gain a little bit, which is funny, which is fun. And now you know why. But generally, you don't lose much from LoRa. And by the way, LoRa is the first of the many. People have optimized LoRa. They have found better ways to do it and this and that. So it has been evolving over the course of the last 2-3 years. And I won't go more into this. There is one thing that they say, that they look at how does the adaptation matrix delta W. I would suggest that if you're reading this paper, do read this section. This section 7.3 I consider very useful because what it says is, it says, let's compare the changes that we made to delta W and compare it to the matrix, like basically how much it's called. There's a mathematical concept called Frobenius norm, etc. Without going too much into it, let's just go into that. What it says is that certain directions are picked out, chosen, and amplified. Those are the dimensions of your low rank matrix. It finds good, real low dimensional embedding or directionality inside the data, and it is pretty good even with R is equal to 4. Now, and I'll just touch upon this rather than this. But this one point, for those of you who know who have strong linear algebra, you will observe that this is quite an interesting point, right? That you have quite an amplification of signal, right? But for that, you have to know a little bit about eigenvalue decomposition, or sorry, singular value decomposition, but we won't get into that. So what is the net conclusion? LoRa is a good idea, isn't it? Now, over this idea, many further refinements have been made. For example, one refinement is the QLoRa. QLoRa is, and I'll just quickly go through it. It is another good paper. What it said is that, see, this, we'll come to that. I'll come to question answers in a minute. So, is that, let's take this idea further. Even the base model, if it doesn't fit onto our machine, what do we do? Right? we need to quantize it for fine tuning. So to that, what it observed, what this paper observes is something remarkable. It observes that the weights, they tend to, if you look at the distribution of the weights, Wij, right, of a given layer, if you look at this and you look at all of these weights, they seem to, if you just do a distribution of that, they seem to be as though they have been sampled off a zero. They seem to show a normal distribution. Means they are mostly close to zero with small fluctuations around zero. Are we together? If that is true, one basic question that we ask is, see, when you quantize digits, let's say that you have a number, let's say 8.96328 2. Typically, if we say that quantize it down to only bring it down to only 2 decimal places, you would do some form of rounding. Now, suppose I say, well, take this value, but squash it down to, well, this was let's say 32-bit float, but I'm giving you only, let's say, a 4-bit float. Now, what would you do? You would take the entire space, let's say of minus infinity to infinity, and try to squash it into the range that 4-bit contains, right? The range of numbers. And you would quantize. By the way, quantization is as simple as, so one very trivial quantization is take a number and just forget its fractional parts. Every number is rounded off to integer, right? That's one form of quantization, but a little bit, bucketization is another word. So if you have 4 bits, you have obviously much smaller number of digits or values to map it to, right? So you're telescoping down to a much smaller number. How do you do that is the magic. So usually you would make uniform buckets, uniform sizes. Now this paper brings about a new concept called the normal float. And it has other ideas too, but this was the big idea, I thought, in this paper. It's called QLoRa, quantized LoRa, right? QLoRa. And what the main idea is that quantize or bucketize around the bell curve, right? So you know that bell curve distribution, these numbers are very rare. -3 and +3 are extremely rare. Most values are peaked here. So make smaller buckets here and larger buckets here. Are we together? Right? Distribute it like that. And so that is your normal float. When you do quantization respecting assuming a normal distribution of weights, you can quantize more efficiently. And so QLoRa has sort of taken over. It's more or less the norm these days. That is the main idea of this this thing. It creates a concept of a normalized quantization. Right? This is the main idea that it brings about. Forward. And so forth. And so I won't go more into it. I think we are out of time. How much is it? 7:21. Yes, we are past the hour. So I would like to open it up for discussion. But before I do it, oh yeah, one more. Let me just recap and see if I missed a point. There is one little point that I did miss, actually. Let me cover it in the original LoRa. One of the things that comes is, and it's a technical point, let's go back to the top. See, remember, you have these matrices, A and B. Why am I not getting my pen? Yeah, let me see this. This is your A, B. I'm just writing it in a big form. How do you initialize it before you train? So you would agree that when you have no data, this is your W naught. When you have no data, your delta W, like how much should it deviate from W? It should be 0, isn't it? It shouldn't have learned anything, right? This should initialize to 0. Right? But then this is made up of B and A, right? Remember, in this picture, this is the way you give A, B. This matrix is decomposed like that. right? So what you do is you set B, set all values of B to 0, all the weights of B to 0, right? Just an initialization. Then no matter what you put in A, B is 0. It starts out with 0. For A, this paper, by the way, it says that use not Gaussian initialization, like initialization. What is Gaussian initialization? Sample of a Gaussian distribution. Are we together? And set all the weights to whatever you sample. Keep sampling and setting the weights, right? All of the weights. So weight of A is sampled of a Gaussian distribution. There you go, right? This is how this paper started out. But these days, what happens is there's an interesting change, I believe, if I'm right. People who are doing the diffusion models, they still tend to use the Gaussian initialization, but there is another initialization. It is called the Keiming initialization, or the there's another initialization, or Keiming initialization. What it says is that an alternative that you can do is you can actually do this. Compute the number of parameters. Let's say that this is a number of dimensions, input dimensions, right? Number of input parameters. And then what you do is you do a normal, not a normal, random. You take a uniform random sampling from the range of, and why this weird number comes from input dimension and plus 6 over n input dimension. So let's say your dimensionality is 100, right? Then 6 over 100, right? Minus that and plus that, you sample from that and you do that. Now, why in the world would you do that? There's actually a very good reason to do this. It maintains something, it's a variance preserving property it has. The output that will be there will show a similar variance as there. And it also addresses one critical issue, which is the question of vanishing and exploding gradients. When you use ReLU, vanishing gradients is more the problem. So suppose you have a ReLU like that. What happens for all negative values below 0? If this is 0, this is negative. For any negative input, when x is less than 0, what happens? What's the gradient? What is dy dx here? Hey, it's flat. Dy dx is? What's the dy dx of a horizontal line? Right? 0. Gradient is 0. Derivative is 0. So you can have a problem of vanishing gradients. In some sense, there's a bit of reason and work why it turns out that He initialization might be a good idea. So, of course, you can take what you like. So, all right, that was one point I'd missed. With that, I would like to end this part and open it up to discussion. Anybody wants to ask a question on record? Otherwise, I'll stop the stream. Go ahead.
So, I don't know if this is mentioned, but how do you usually find it in terms of
Oh, how do you determine? At this moment, empirically. You play with it and see at what moment you begin to lose too much. Or another way of looking at it, see, one intuition that I carry for delta and its intrinsic dimensionality always is think autoencoders. You ask yourself, what is the lower latent dimensionality that is optimal for the autoencoder? Right? At what point if I go below that, I start losing a lot of information.
So it's like in PCA, so it's like the number of
exactly. So in PCA, what would you do? You would look for the elbow method, right? The scree plot, the proportion of variance explained, right? So its generalization, think of its generalization. Pretty much that. Yeah. That's the way I think about it intuitively. Yeah. So it's an empirically determined thing. Every data in this AI field, right, ultimately data is king. Or another way to put it, there's this no freelance theorem. Right? For no one model will ever be great for all data sets. Or the basic intuition being every data set represents a different generative dynamics behind it. The dynamics may be simple, it may be complex. You don't know a priori. The only way for you to determine what the underlying dynamics is behind the data that produce the input output, right, is to play with it and empirically determine it and model based on that. So it's an empirically found thing. Okay. All right. Any other question on record before I stop streaming? Srinath.
Like LoRA, is there any other advancements over LoRA?
Oh, many. In fact, why don't I do that on the, in this portal that I mentioned, I will give you let me just put it this way. Do you see this entire folder of research papers? Yeah. They're all about the LoRA methods, right? And various perps, right? So rest assured that you can stay entertained for a week. All right. Any other questions on record, guys?
Asif, right. There are a couple of questions in the chat.
Yes, please. Would you
how is the rank for the last column of the matrix determined? That was it's probably the question came up when you were walking through with the example.
Last column of the matrix. Which one? So I suppose. Oh yeah, it is the same question. How do I determine the rank R here? This little r here. And if I understand the question right, you're asking, how do I determine this r here? Let me expand it. How do you determine this r? And sorry, this r in there. How do you determine? See, the output, you don't, like, this is not in your control. It is in the architecture. If you're creating a LoRA for this particular transformer, you have to basically go and see what is the output. The input and the output are not in your control. So D and H are not in your control. The only thing in your control is R, right? And this is what you play around with, and it is an empirically determined thing. So this question is the same as what this gentleman asked, that R is in a way your proxy or the determiner of the intrinsic rank of the matrix in some sense, right? Play with it and then you'll know. Right? But what I find very surprising, and I suppose I should have talked a little bit more about it, is when you look at the ranks, it is shocking how small it is. May I present you one particular table? Actually, I should have talked about it because it's so surprising, so very surprising. Look at this. Look at the rank here. Pay attention, please, to this. Right? You go down to rank of 2, and do you observe that sometimes the result actually tends to improve, right? And you rank 4, rank 8, you're looking at matrices which are fairly high dimensional. Now, one more thing is that these people, they tend, when you look at the transformer, the query weights and the value weights and the key weights, these people, I believe, they tend to take only 2 of the weights and LoRA. They don't tend to take all 3 at the same time. It's a choice, just for simplicity. They did that. Yeah, look at this. You can go down to rank 1. That is shocking. Right? So rank 1 is, imagine the spiral that I talked to you about. How far you are from the origin of the base of the spiral. It's literally like that. You're basically saying that this high dimension space, in some sense, is a way, the physical intuition that I carry in my mind is, you're basically saying I'm reducing it down to a spiral, right? The whole input needs to get squashed to some point in my spiral, right? Okay, guys, these are hand-waving intuitive arguments, the 2 dimension, and you can see that. All right, second question.
Yeah, I think second question is pretty much related, so we can skip that. Thanks, Asif.
Okay, all right. Patrick, you look as though you have a question. No. Nothing.
How much do you actually use moving from the LoRA to LoRA? And can we get away with
See.
something really, really small?
QLoRa. See, how much do we, the question is, how much do we lose moving from LoRa to QLoRa? Case by case, sometimes you lose quite a bit. Right? See, the thing is, it depends on your domain problem, Patrick. As you know, in some domains, losing 5% may not mean much. But in some domain, 5% is noticeable loss. Like the users can tell that this is a much worse model. So it depends on the domain to domain, task to task, and so forth. But generally, I would say not much, because guess at this moment, what choice do we have? We are all using QLoRa's, isn't it? No, because that's all we can fit on our 4090s.
And for embedded devices.
Or for embedded devices and so forth. Srinath, you have another
What is
question.
the weight type? The weight type that you have in the table, what does that signify? The second part?
In this table?
Yeah.
Oh, which of these are you fine tuning? So the first row is you're only doing LoRa on the query weights, in the attention matrix. Remember, given an input, you burst it out into the query vector, the key vector, and the value vector. So they're saying leave the key and value alone, just apply it to the query vector. The second one says, okay, apply it to the query and the value vector. The third one says apply it to everything, even the output vector, the output matrix. Right? So sorry, weights, because those are matrices, right? X goes in, what comes out? Query vector comes out. So there's a matrix that does the transformation. That is the query weight. Likewise, the value weight, the key weight, the output weight after that, because even the output you transform a little bit, take it through a few hops there. So that is that. Now, there are a couple of things that I may have wanted to talk about, but it needs a little bit of linear algebra understanding. But maybe I'll talk just a little bit about it. There is something beautiful. One of the crown jewels of linear algebra is something called singular value decomposition. It tells you a lot. In fact, the early recommendation systems, like the ones that won the Netflix prize, were derived from singular value decomposition arguments. It basically said that given a big giant matrix, just like you can take a number and decompose it into its prime. And when you decompose it into its prime, you sort of feel, now I know this number, right? 21 is 7 times 3. These are the prime factors of it. Right? So in the same way, if you take a matrix, you can break it up into smaller matrix. And 3 matrices, U, D, and V. And the D is the in-between diagonal matrix. And usually what happens is that the diagonal matrix will have lots of values along the diagonal axis. But along the diagonal axis, a few values will be big, the rest of the values will be tiny. So what it is telling you is that the data actually lives in a much lower dimensional space, because you can zero out the tiny ones and therefore look at data as a low dimensional space. And that's what, in a way, the intuition comes from that. So there is you see all of these linear algebra things in the background, but let me not get into that. All right. So with that, I'll stop the streaming and we